All right, so from your reading and from the video, what you're seeing for Le Chatelier's principle, or Le Chatelier's principle, is that all equilibrium wants to do is get back to equilibrium. So reaction at equilibrium wants to achieve equilibrium once again because it's the most stable place that it can achieve with a proper ratio between its reactants and products. So if we stress the system, what is a stress? What's an example of one? Shout it out. Heat. Or temperature, changing temperature low, so like cold. What else? Changing pressure. What else? Diluting, so like changing concentrations. Adding things like reactants or products. Say again. Changing the volume. So those are actually basically all the things that we could do to stress the system. So what we're going to have to state is not just how is it going to change the equilibrium position. What I mean by that is it going to shift left? Is it going to shift right? Or is there going to be no shift? We've explained why. But the why part is hard to wrap your tongue around sometimes in a concise manner, because you guys will, on your test, will write me a paragraph about why something changes, but you don't need to. You need to kind of consolidate and say exactly what you need to, because from memory, 5 people said something beautiful in their FRQs and then contradicted themselves in the last sentence, right? So the more you say, sometimes it's not exactly the best thing for your getting points. So make sure you're not contradicting yourself by like just telling me all of your knowledge. Just say what you need to say. Okay. So when we say that the position is shifted, the equilibrium position is shifted, it just means there's a change in the concentration of reactants and products. No change in K. The equilibrium constant itself, the K value, is not changing. It's not that we're changing the favorability in the forward or reverse direction. There is only one condition that will change K, and that's temperature, which is going to be on the next slide for us. But when we talk about why something is shifting, we want to mention the rates of the forward versus the rates of reverse reaction. So rate forward versus rate reverse is going to be a common term that you'll be using in your explanations. Okay, so the first example, changing a reactant species. If we're talking about adding a reactant, you guys tell me which direction is most predominantly affected. So which forward direction or the reverse direction? Forward reaction or the reverse reaction, which is most heavily impacted? Forward, because reactants force the forward reaction to occur. So you would say something like, or you would note that adding a reactant species speeds up the rate of the forward reaction, because more collisions, right? Remember, we always talk about collisions as it relates to rate of reaction. Therefore, dot 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 means therefore. So therefore, the equilibrium position will shift right. So when we add a reactant species, we're adding something that's going to cause more effective collisions in the forward direction. Therefore, it will shift right, because essentially, as we shift right, we're making more what now? Products. So I'm just going to continue, but you don't have to write this part. This is the blah 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 part where we can keep going for days on how to explain this. But as you make more products, then the rate of the rate of the reverse reaction will also speed up, because you've made more products, right? Products react with each other, they reverse the reaction. Reactants react together, they go forward, and then vice versa. So they're constantly, it's dynamic, right? They're constantly back and forth, back and forth, back and forth. It's just this first part, increasing the reactants, will immediately speed up their forward reaction, which will cause it shift right. But remember how we've always talked about predicting which way a reaction will proceed by looking at Q versus K? Okay, that's the same thing. Open it up. Just open it up. Oh, somebody's like jostling with candy trash. Okay, so this is caused because when you increase reactant concentration, what does that do to Q? What does it do? Increase or decrease? Decrease, because where are reactants in Q? The denominator, right? So if you increase the denominator, Q gets smaller, right? So Q is low, so therefore Q is less than K. So if Q is less than K, which way do we proceed? To the right to make more products, right? So all of this relates back to the proceeding left and right as we stated with Q. All right, so that, I didn't finish this, then the rate of reaction will increase, and then come to equilibrium again after some time of back and forth, back and forth, back and forth. Okay, so then try to use that same phrasing and do it for the second one here. It depends on how elaborate the question kind of is asking. Many times we'll just state increasing concentration of a reactant will speed up the forward reaction, cause an equilibrium position to shift right. Like, that's it. So you guys are saying speeds up what? Rate reverse, okay? Because what? More collisions in products or something like that. Therefore, so more reactants will be made, right? So we are shifting the equilibrium position shifts which way? Left, as more reactants are made, so products are consumed to make more reactants. So, and this is all because what have we done to Q artificially by adding product species? We've made Q greater than K, so to allow Q to meet equilibrium again, or allow equilibrium to be reestablished, we need Q to what? Decrease, and so the only way you're going to get Q to decrease is by taking away products. So making them get consumed. As they get consumed, as they react, they are consumed, and as these are produced, the Q value equilibrates with K. You good here? All right, so same story, but it's going to be talking about not speeding up a reaction, but slowing down a reaction because we're removing species. So if you have a product and you force precipitation by adding a common, I'm going to call it a common ion. We'll elaborate on that in a second. So if you force a precipitation reaction of a product, or somehow remove a product, it's difficult to remove a product because it's like mixed in with everything else. So you have to find a way to like selectively precipitate a product, like an ion, like silver. It's going to precipitate with a lot of things, so you could definitely do that. Then we've decreased the numbers of products. So decreasing product concentration decreases the collisions, therefore decreases the rate of what? The reverse direction, right? So eventually the forward forward reaction will occur naturally at a higher rate than the reverse because there's just not enough stuff to do the reverse reaction. There's not enough collisions. So the forward reaction proceeds, therefore changing the equilibrium position by what? Shifting which way? Shifting right, because we're going forward. So, the elaborate nature of some of these explanations kind of holds us back, but if we just have to think about, hey, which way am I going to shift? Your job is to think about, here's my stress, my job is to counteract that stress or counteract that change. So if I take away a product, what do I want to do? Make more products, right? The only way you're going to make more products is going towards products to make them, which is shift right. So if I take away a reactant, oh no, got too few reactants, what do I have to do? Go back towards reactants, so we're going to be shifting left. So sometimes it's just like, hey, which way do I shift? What does it cause? Sometimes I need to explain why. So decreased reactant decreases the rate of, anybody? Forward direction, therefore shifts equilibrium position to, anybody? Left. Okay, and so there is constantly this Q versus K debate. Occasionally they'll say like, explain with reference to rates of reactions. That's kind of what we would be doing. It just says explain and tell me which concentration increases or decreases over the course of the reaction, then you'd be referencing a reactant. So it kind of depends on how it's raised. Okay, so those are concentrations. Changing pressure, this is really going to only affect gaseous equilibrium examples. So we don't necessarily just straight up change the pressure. We usually change the pressure by changing the volume, because what is the relationship between pressure and volume? Is it a direct or an indirect relationship? So as I increase volume, take your box of air, increase the volume, what happens to pressure? Decreases, right? So it's a what relationship? Indirect relationship, right? And that's Boyle's law for you, right? So you need to think about what's really the stressor here. If I change the volume, it's going to change the pressure. Well, remember, and this was on our test most recently, what is technically causing pressure? Collisions with the container wall. It's not necessarily with themselves, it needs to be like referencing the container wall. So if I change the number of collisions with the container wall, then I need to find a way to modify the collisions with the container wall again. So if I decrease the pressure, I'm like, oh no, don't have enough collisions, I need to make more collisions. If I increase the pressure, you're like, oh no, I've got too many collisions, I need to make less collisions. So the only thing that's going to give you information about that are the mole ratios of a reaction. So if I have like formation of ammonia, as an example, and this is all gaseous, and I change the volume, I decrease the volume, what does that do to pressure? Increases pressure, and essentially that means you have more collisions with container wall, and so your job is to counteract those collisions. So do I want to shift towards 4 moles of gas, or towards 2 moles of gas to counteract this stress? 2 moles, because I already have too many collisions, so I don't want 4 moles of gas banging around. I want 2 moles of gas banging around because there's less moles, less collisions, lesser pressure. That has counteracted the stress. So shift in direction to lower the number of collisions. Which in this case, 2 moles versus 4 moles. And remember, they have to be gases, can't like have solid moles bouncing around, would cause a shift right. Yeah. Mm-hmm. And then say because they'll have lower number of collisions, that'd be great. So yeah, I reference it here, but let me elaborate here. Increase pressure, so shift direction to lower the number of collisions, which would be caused by the lower number of moles of species, and therefore that's why I'm referencing the 2 to 4. So this overall would cause a shift right to reestablish equilibrium. So therefore, K is not changing, the equilibrium position is though. Okay. So opposite of that, if I have tighter volume, what happens to pressure? Increases, so we shift to the side with, sorry, I went the same way. Increased volume causes what pressure? Lesser pressure, so I want to get pressure back up, so I go to the side with more moles, so more collisions, so higher pressure again. Are we okay so far? Some people are shaking their heads. Okay. So the other condition with where pressure would be included is actually a no shift situation. So what is an inert gas? Before I move on. Okay, so any examples of inert gases? Say again? Nitrogen's an inert gas. Argon, like a lot of the noble gases, are also inert. Inert means not reactive. Helium. Okay, so what we would have is if we have an inert gas being added, it's a gas that's not reacting or not present within the equilibrium system. Now, of course, this nitrogen would be relevant to this example I just did up here because it is part of the equilibrium system, so it's no longer inert. It's like a part of the reaction. But if I add a neon to this reaction, it's going to do jack squat, right? It's not going to do anything because 1, it's inert, it doesn't react, and 2, it's not an equilibrium reaction. And so what we'll say is it increases the total pressure because more stuff, more pressure, but it does not increase the partial pressures. And that's important because Kp is all based on what? Partial pressures, right? So like partial pressure of ammonia over partial pressure of the two reactants, if I don't change their partial pressures, do I change the K? No. How do I get, how do I relate P total to partial pressures again? So this, I heard summation. Okay, so P total is equal to partial pressure plus partial pressure plus partial pressure. There's another way though. Mole fraction. It's been a while, but we know this. P total times what? Okay, remember like X was our mole fraction variable, so it's moles of A over total moles, and that would equal PA. That would equal partial pressure of that gas A. Do you remember that? Probably review, because this is going to be like a piece of the puzzle that could be used to find one of these, which would be then used to find K. Alrighty? Can I go forward? Okay. So the last situations are, the fifth one's I think the most important because we need to talk about how this does impact K. But overall, catalysts, they do not shift equilibrium. So these would be a no shift. Because when you have a catalyst, it's going to speed up the forward reaction and the reverse reaction in such a way that collisions occur to meet oxidation energy in both directions. So we're allowing these to meet oxidation energy, we're allowing them to react. The rate of the forward will continue to equal the rate of reverse. Even though they're both sped up, it will continue to equal the rates to each other. And then adding or changing temperature, it's going to be the big guy. So I'm going to let you read that first before we get started. You can write down stuff too. I'm going to elaborate. Right, so changing the temperature is going to be your only stress that can actually change the value of the equilibrium constant K. No other change yet has actually changed the true value. So, like we stated with rate law constants, K, little k, we said higher temperature meant what for K, little k? Higher little k, because what happens to the rate? Speeds up, right? Well, temperature and the thermodynamics of a reaction are very side-specific. They're unidirectional. You can't have both endo and exo at the same time. You can only have one or the other. So in that case, we will be speeding up one reaction more than the other reaction just by the nature of how the energy is consumed. So if I have a reaction that's endothermic, you can see I put the energy into the reactants. Let's not call energy a reactant. Basically, the energy is consumed in the forward direction, but produced in the reverse direction, just because of the nature of how endothermic works. So if you increase the temperature, the stress is I have too much energy in the system now, right? Temperature is related to kinetic energy. So if I increase the kinetic energy, increase the temperature, I need to find a way to consume that energy. The only direction of this reaction that consumes energy is going forward, because I'm consuming 100 kilojoules for every mole of A and mole of B. So I can't reverse the direction, because that would just release more energy and it would exacerbate this problem. Does that make sense? Okay, so how do we say this? Versus saying all that, the phrase you should use is right here. And it stops you from counteracting or contradicting yourself. So if you have an endothermic, if you have an increase in temperature, the reaction that is the endothermic direction is then favored. You'll notice that I don't mention forward or reverse here. This is my cop-out. This is how I can say it without noting a direction as well. So essentially, favors the endothermic. Can you see that? Oh, weird. Okay. Okay, we're gonna move on from that ghost moment. Okay, so if it favors the endothermic direction, in this case, this example, which is the forward direction, because essentially it's going to make the rate forward greater than the rate reverse, and this is a permanent change. There's no like, oh, I'm eventually going to get back to the same place where I was. This is a permanent change. You're making the forward reaction occur at a much faster rate than the reverse. So we essentially permanently, we permanently push it so there's always more products than reactants. So if we push it to be this, there's going to be more products than reactants. What does that do to K? It increases K. Simply because this endothermic direction was forward to be pushed to make more products, and that it results in a higher K value. Question?
So is it like safe to assume that at all times if the 1,000 like 100 kilojoules if it's in the reactants that it's favorable to the endothermic and if it's in the products it's favorable to the exothermic?
Yeah, and that's what you guys should know that. If energy is in the reactants, it's endo. If energy is in the products, it's exo. Because we're consuming energy or absorbing energy is another way to say that, or releasing energy as a product. So then I want you guys to kind of use that same terminology, but answer how, in this example being exo, how would you explain that? How would it change K? So how would increasing the temperature affect this reaction and affect the K? Taz, what you got? Am I decreasing temperature?
Oh, would be favorable in the reverse reaction?
Because
You have your energy on the right side, and if it goes to the reverse reaction, you're going to be increasing energy to the reactants.
you're going to be, okay, we can't say that. I know what you're saying, but we can't say it that way. So that's what we're working on, is how to phrase these appropriately so you're not like babbling on in your head. So we want to try to use this phrase. Okay, so increasing temperature favors the, no, you still will say this. The endo, I'm going to say direction, but in this case, reaction and direction means the same thing, because the endothermic reaction in this case is this reaction. It's C plus energy yields A plus B. Like, that's the endothermic reaction, where in this case up here, this was the endothermic reaction. It was A plus B plus energy yields C. So we can still utilize that same phrase, which makes it nice. So increasing temperature favors the endo reaction, which is the reverse reaction. There you go. That's what you want to say. Therefore, what does that do to K? Okay, so therefore K decreases because what happens to concentrations of reactants? Products decrease.
Just that one, what?
Say that more time. you guys are doing this example that Andrew helped me get on board. Thank you. So I know the question is how will the chlorine change, but there's a question that comes before that you can consider, and it's which way will this reaction shift? And that's then going to prompt you to be only concerned about chlorine. So try those first. We don't say it's on the reaction side. This is the whole system, just like a container. The whole system. We are All right, what are you guys saying for phosphorus trichloride? All right, hold on. Which way does it shift? All right, so increasing concentration of PCl3 causes a shift right, and that's because rate, what speeds up? Rate forward speeds up, just as a side note. Okay, so then, what did you guys say it does to chlorine? Okay, raise your hand if you say decrease. Raise your hand if you say increase. Okay, most of us say decrease. Good, so chlorine decreases because it's consumed in the forward direction. I like to skip words sometimes. So if you're shifting right, you're taking away products, you're consuming them, and you're increasing you're taking away reactants because you're consuming them. You're increasing products because you're producing them. Clear? All right. Does that change K? No, just position, which is the relative ratio of reactants and products. Eventually, the ratio comes back the same because if that changed, then the K would change. All right, PCl5 is added. Shift which way? Okay, so shift left, and then what would it do to chlorine? Increase chlorine because is it reacted or produced? It's produced in reverse reaction. Okay? Temperature is low. Yeah. It's not asking about specifically number of moles of all products and all reactants. It just wants to know that one specific species. So if you add this, it's going to cause the reverse reaction to occur more predominantly, which means that both of these increase in concentration. So if you produce chlorine, it's therefore going to increase its concentration. And I didn't put increase, so there's increase. Is that good? They all have what? Some of them have no shift because of the same number of moles on both sides. We'll get to those examples in a second. Okay. So decreasing temperature. So if we, like we said earlier, increasing temperature favors the wet reaction. Endothermic, because increasing temperature means I have too much energy in the entire system. I need to find a way to consume it. The only way we're going to consume energy is if it's showing the endothermic direction. So how would you state this one? Okay, so lowering temperature favors the exothermic reaction, which in this case is, therefore, I'm going to try to write this neat for my viewers at home, favors the exothermic reaction, which is the what? Why do we say forward? Because this reaction has a negative on its delta H, meaning it's already written in the exothermic direction, which is the forward reaction, which is the forward direction. So as you react in the forward direction, what happens to chlorine concentration? Okay, so then chlorine concentration decreases because it is going to be consumed in the forward direction. Okay, keep going. PCl3 is removed. Which way does it shift? Okay, so to decrease a reactant species, we'll shift left, and what will happen to chlorine? It will increase because we're shifting towards it, we're producing itself. Neon gas is added. No shift because it is inert gas, good. Volume, and this is when we need the reaction again, volume is increased. Okay, so the volume being increased, volume itself doesn't help us a whole lot, but what does the volume affect? Pressure. So what is this one doing to pressure? Say again? It's decreasing pressure, good, okay. So increasing volume causes a decrease in pressure, so there are, okay, so a low number of collisions with the container wall. And which way do we shift to counteract that? So, so yeah, we need to look up here, right? So what am I looking for now? Like coefficients, look for more moles. So there's 1 mole, 1 mole, 1 mole. So we're going to shift to which direction? Left, because there are 2 moles of gas there. So shift left to increase the pressure by nature of moles. Yeah. Something like that. Okay. Overall for Lestat, can you predict which shift will occur? Okay. And explain increasing or decreasing concentration. Okay, the explanations will come better to us, okay? So I think I'm going to do one more example and then we're going to move on from here. I'll show you these graphs Monday, but essentially they're showing the changes occurring. They're showing an increase or decrease in reactant. But then at the end, you'll notice that both of these lines become what again? Equals or zero slope. So they are eventually getting back to equilibrium. So we'll talk about this a little bit more. And then go ahead and grab laptops. So that's the half of the class. I'll specifically answer these questions with you guys as we get talking, okay? And if you guys can, actually, there's lots of space. Try to be half and half. So if you go to my homework webpage, that's kind of where we're getting to. So if you've not grabbed your laptop, go grab your please. We're going to get to that in just 1 second. I do want you to write down this for Le Chatelier's before the laptop's taking a hot minute to get on. So the common ion effect is something we'll discuss a lot more when we do talk about KSP next week. But essentially, it is a way of reducing solubility. So if I reduce solubility, do I mean that I make something more aqueous, or do I mean I make something more solid? Right, more solid. I'm reducing its ability to dissolve. So if I have like an example of barium hydroxide, solid, dissociating to 2 ions in their aqueous form, what I could do is I could limit barium hydroxide solubility by throwing a common ion into its system, into its equilibrium system. So if I added like potassium hydroxide, well, potassium ion's not in equilibrium, nobody cares, but this dissociates into OH minus ion. So essentially I've added a common ion, which is OH. What would it do to this equilibrium? Shift left, shift right, or no shift? It would shift left because I've increased by the common ion effect. I've increased the OH concentration. It's now at this equilibrium. I'm going to have a sped up reverse reaction, which would make more solid, which has essentially done what to its solubility? reduce its solubility. So that's something that we'll call the common ion effect, and we will work with more. And I have 2 questions I want us to answer before we jump into this Le Chatelier simulation. So talk to the person next to you about the 2 questions up here. I'm going to scroll down just a little bit. All right, back to me. All right, everybody in unison, which way will this shift? I heard a lot of people say right. Does anybody have a different opinion? Kathy? No, that's you're thinking about the common ion effect. This is not an ion one. This is all gas, and solid. Those would have the aqueous. But I like how she's thinking outside the box, because the answer is no shift. Okay, why? It's a solid, or solids in the equilibrium expression. Do they impact many things? That's sneaky and low, I know, but no. It does not impact the equilibrium, because this is all gaseous and you don't have solids in the equilibrium. Okay? What happens to the mass of A if more B is added to that reaction vessel? Come on. Okay, Kui, what are you saying?
It'll decrease.
Why will it decrease?
Because since you have more B and the reaction forward will bring up the reaction forward will increase. It would mean A is consumed before it's done.
Good. So they're serving as reactants. Therefore, we would consume those reactants. And though it is a solid, you can affect its you can affect its amount by taking into account if the effect is causing a shift left or shift right. So increasing B will cause the reaction to shift, forward, left, therefore consuming both reactants and producing products. Okay, and then in our lab, eventually, on Monday, you'll see there's a situation where we add liquid water. We'll add water and we'll dilute a solution, right? Remember that water liquid, like pure liquid, is not in our equilibrium expression, right? But it can impact ions by making them more dilute. So if you have something and you've diluted their concentrations, you've effectively changed the concentration of either reactants or products, or both. Some you might, like maybe you have 4 ions in the reactants, 2 ions in the products, you would have affected the 4 moles of ions more. So therefore we would need to see how we shift the reaction equilibrium. Okay, so go to my homework website. Who's there? Okay, so in an effort to let you see this in a little bit more depth, especially with examples, I'll come right back to that slide here. So you're going to the simulation that's underneath the homework part of the website. That's actually where I was going with this. And it looks like this. It's like this. Oh, dang, it's right there. Okay. So the first part's reading. I do want you guys to sit and just kind of read and take in some of the examples that they're giving you, especially with the blood. They like to use some real life examples, like on your AP exam, they'll tell you like a scenario, you don't want to be confused by it. And after that, the animations person stopped updating their sims, so I videoed it. So I do want you to look at this YouTube video of me playing the simulations, and then you will answer questions that relate to that. Okay? So there are 3 of those. And then reading again. Okay? Reading again, I made a comment because that was the kind of important part. And then I'll see if we get to this part 2. Let's see where we are in like 20 minutes. Go. Let's get started on one of those, okay? Reading, and then video of me playing the simulation. I'm sorry. And I'm gonna leave all the homework page up, and it's because like January and Wednesday convention, like everything is there. Keep making it text smaller and smaller so you can't see it. But I'm trying to make that page not so long. I know for a minimum, I know that we're gonna do like the reading, the part 1 and the part 3, because the part 3 has AP questions on it. If we don't get to another portion of it, we can next week, okay? So for sure, part 1 and part 3. And I'll play whatever music I have on. You want holiday?